Presenter, okay. Perfect. Good.
Please, Alexandra will share the session, so you can start when she introduces you.
Okay,
Yeah.
perfect. Yeah.
So they're having coffee breaks now, if you want.
Yeah, I have to check that everything looks okay.
It's the right one.
Yeah, it's the right one. It's the right one. I was making just some changes, but I am checking that it looks good. Okay. Yeah. Okay. Let's see. Problem optimization. Huh? I think so. I think. Okay. The problem, I had to, I made it a bit longer. I had some slides explaining what is stability, because I suppose many people here won't know what is stability. I hope it fits. I will also introduce, as these people do tensors, the relaxation as a 3 tensor. It's a way of, you can also see it that way. Yeah. We are 5 minutes past the time. Shall I start? Okay. More people coming. Okay, it's okay. Take your time. Yeah.
Okay. Sorry for my delay. So we have Alejandro Gonza lez Nevado from here, from Constance. He's speaking of a method for establishing asymptotically accurate bounds for extreme roots of
Eulerian
Eulerian polynomials using polynomial stability preserves. The floor is yours.
Okay. So thanks a lot for being here, and thanks a lot for the opportunity to the organizers. I am the last poema, so I am very happy of being able to transmit what I did within the previous network to the new generations. Okay. So let's start. As you can see, the title is actually quite descriptive if you know what everything means. Huh? Once you know that, you know a lot already. So we are going to study some method to find, we have to say what exactly is, how much accuracy can we expect asymptotically for bounds of the extreme roots. One call expect what is that. Of Eulerian polynomials, we have to introduce them. They are very important in combinatorics. They also appear in analysis. They appear in many places. Using polynomial stability preservers. I suppose less people will know what is a stability. And once you know what is that, you know what is a preserver. Okay, so we will do that using a relaxation that Marcus introduced some years ago. And we will see how the relaxation helps us understand better the roots of these polynomials, and at the same time, we will use the polynomials to test how good is the relaxation. So this goes both ways. Okay? Yeah, so let's start. So the object that interests us here are real zero polynomials. The real zero polynomials, how many people know what is a real zero polynomial here? Okay, so not many. So, okay. These are very important polynomials because you actually know what is a real zero polynomial in one variable. A real zero polynomial is a real rooted polynomial. This is a generalization to several variables, okay? So now, when you take something multivariate, you look at each line, and you take restrictions in every line, and all the roots of these restrictions have to be real. So you have real roots at each line through the origin, right? And these sets, we will see a picture soon, and things will be clear. These sets, they define some important sets in optimization that are the rigidly convex set, which is the Euclidean closure of the connected component of the origin, because we will see that they separate the origin from the rest of the space. Maybe you have not heard about real zero polynomials, but maybe you know about hyperbolic polynomials. If you do optimization, you know what they are. And they are the projective version of real zero polynomials. You can transform from one environment to the other. This is the affine version. We use the affine version here because it is easier to visualize. Okay? So now let's see a picture of these two concepts. So the blue thing here is a cubic real zero polynomial. So imagine that here is the origin, right? So when you take any line through the origin, the line will cut this set in 3 points. except here, right? If you take this line, it will not cut in 3 points because it will only cut in 2, the blue set, I mean. This is because there is a root at infinity, or because you can also see that this polynomial, that this restriction becomes a degree 2 polynomial there. The red thing is also real 0 polynomial, is what we call an interlacer. We will see soon that they are important. But this will be a quadratic real 0 polynomial. Okay, and the thing, the connected component of the origin, so so here you have to subtract the 0 set, right? You take the whole space, you take the 0 set away, and then the origin will be separated. So the connected component of the origin is this set. This is the rigidly convex set of the blue polynomial, the blue cubic. And as you see, the rigidly convex set of the red polynomial includes the rigidly convex set of the blue polynomial. We are interested in representing these rigidly convex sets in ways that we understand better. One class of objects that we understand very well are spectrahedra, right? Spectrahedra, they are very used in, they are very important in optimization, to do semi-definite optimization. Spectrahedra are defined as the, so here you have this set S will be a spectrahedra if it is the solution set of this linear matrix inequality. This is a linear matrix inequality, and this defines the spectrahedra S. When you take the matrices AI to be real symmetric, and usually you also expect this matrix to be positive semi-definite. So this thing is a linear matrix polynomial, and we will see them appearing quite often. Then in this context, the big problem is a big problem in real algebraic geometry, in optimization, is this challenge. So there is we think that every rigidly convex set can be represented in this way. The generalized Lax conjecture there was a Lax conjecture that was for 2 variables, and we know that this is true. We also know that the generalized Lax conjecture is true for some polynomials that come from combinatorics. And we will see that exploiting combinatorial information is important and interesting. For more than 2 variables, the problem becomes more complicated because you need a cofactor. For 2 variables, you can directly represent these polynomials as the determinant of an expression like this. For more than 2 variables, you will need bigger matrices, and there are papers that says that these matrices have to grow a lot, very fast. So it's a problem, because you have to find a very big cofactor if you expect to be able to do that with each polynomial. So in order to do that, as we don't have exactly a representation all the time, we are going to define a relaxation. What is a relaxation in the context of optimization? A relaxation is a set, a bigger set, that is going to contain our rigidly convex set. How do we define this relaxation? Well, we start with our original polynomial, that is going to be a real 0 polynomial, and we are going to normalize it so at the origin is 1. Why we normalize it? Well, because then we are going to define its logarithm. And if we normalize it, this expression makes sense, because then this has a positive degree, and then this stabilizing degree. So you can define this series. And when you define this series, using the series of this polynomial, you can find these numbers here, and these numbers are going to define a linear form from the linear space of real polynomials to the reals, right? Now you have this linear form, and you are going to build also this matrix using monomials of degree up to 1, the monomials of degree up to 1. This is going to call the mole matrix of the relaxation, is what is going to allow us to define the relaxation. So now in the mole matrix, you take, so this matrix is, you just take the exterior product, right, of these 2 vectors. And you can see it also now what happens here as a 3 vector because you could take now another exterior product and you will have a 3-vector, and then you apply the linear form in each entry. So you apply it entry-wise. You can see it also this way. So you define this matrix, and then you apply entry-wise the linear form. And now you also define, and in this way you define the initial matrix, and then the rest of the matrices that we are going to work with are this, in which you first multiply the mole matrix by the variable xi, and then you apply again the linear form entry-wise. And you do that for all the variables, right? And in this way, you build this linear matrix polynomial. And with this linear matrix polynomial, you can define this spectrahedron. This matrix is positive semi-definite. Marcus proved it. This is positive semi-definite. So then if you use the Helton-Binikoff theorem, you can actually prove that we are calling it a relaxation. So we define it, and then we want to see that it's a relaxation. You can see that this actually defines a relaxation. The rigidly convex set of the original polynomial is included in this spectrahedron. So we have indeed a relaxation. And now look at this relaxation. This relaxation, first of all, as I said, people here work with tensors. So you are going to say, well, where are the tensors here? It's a 3-tensor. Now you slide it, and you want to find a way to construct a polynomial out of a 3-tensor. It's a symmetric 3-tensor, right? So you can choose to slide it as you want, but you slide matrices. And to each of the matrices in the slide, you multiply it by some variable, then and then you take the determinant, or you study the linear matrix inequality. So it's a way of obtaining a linear matrix inequality out of a tensor. And this carries some information about the original polynomial. But this tensor this linear matrix inequality is not big enough, because as I told you before, there are papers that tell us that if we really want to express this set as spectrahedra, we need very big matrices. This is proven that if we want to do it in general, matrices the size of the matrices have to grow. And these matrices, this linear matrix inequality, have the size 1 plus the number of variables of the polynomial. So if we want to be able to get closer to this, we need to find ways to increase this linear matrix inequality. You can try several things. You can try to just look directly at the tensor and try to increase this tensor, adding more monomials, right? When you multiply it there, you can try to add more monomials. But you have to remember that you need your initial matrix to be positive semi-definite. So the origin is included here. And this is a problem. We will see what is a problem. Another thing that you can try, and it will be less problematic in this sense, is to increase the amount of variables of your initial polynomial. Then when you have more variables, this linear matrix polynomial grows, which is what you want. But you want this variable to be added in a way that you can recover easily your original polynomial. Which the most naive thing that you could try is to do a Nui type transformation. This here you will say Nui, but you cannot see what is there. Huh? What you do for that? So you take your original polynomial, you can try to do this. Huh? You can try to take your original polynomial, and then you can try to add a new variable, y, taking p plus y, the first Renegard derivative of p. The Renegard derivative of p is defined for multivariate polynomials. It's like taking derivatives from infinity. This is so you homogenize, and then you take the derivative with respect to what you homogenize. But you can do this for every polynomial. And this derivative is an interlacer. And there is a theorem that tells us that when we do this sum for an interlacer, what we get here, this p tilde, is a real zero polynomial. So we can apply the relaxation to this p tilde. And we could try, in this way, we could try to trick the relaxation to tell the relaxation, okay, we are giving you more information. You have to think about that information theoretically. So we want you, the relaxation, to give us more information about the polynomial. But the relaxation is very clever, and the relaxation tells you, no, my friend, what you are doing here is trying to trick me. you can do this for every polynomial, and you are not giving me any new information. So the relaxation, when you restrict back to your original set, you cut with the y equals 0 set, the relaxation doesn't change in this case. So this method is too general. It happens for every polynomial. It doesn't give you any new information. Problem. So we require more elaborated transformation. The relaxation wants information. The relaxation is hungry for information. How can we do this? Well, now we will have to look at more specialized polynomials. We will see that soon, but I promise to tell you what is stability, what is the meaning of a stability and what is a stability preserver, right? So stable polynomials are also a very important class of polynomials, and they are related to real zero and hyperbolic polynomials, because sometimes you can recover a real zero or a hyperbolic polynomials from a stable polynomial. This is what we will do here. So a stable polynomial is a polynomial. Now we allow our coefficients to be in the complex numbers that verify the following. Verify that for this set, the set where the imaginary part is bigger than 0, P is equal to 0, or P of x is different from 0 whenever x is there. This is a stable polynomial. It's an easy definition. It's not very complicated, right? For these stable polynomials, there are some problems, some big problems that comes from complex analysis, these Li, Yang, and Paul-Yashur programs, that we want to understand which transformations in these polynomials preserve stability. But we know that for linear stability preservers, thanks to the work of Porcher and Branden. And linear stability preservers look something like this. So you will see why I use this transformation. There can be other transformations, but this is an example, right? So you start with a stable polynomial here in n variables, and then you do this transformation that is linear. As you can see, it's linear in the polynomial. So you do a linear transformation. You can see that it verifies some properties of one theorem of Porcher and Branden. It's in a paper that is called in this way. You can find the paper easily. It's a really famous paper in the area. And then you see that if you start with a stable polynomial here, this new polynomial is stable. So you can apply it again, and then you get a recurrence that verifies that each element in the recurrence is real stable. Which recurrence is this? Well, it turns out that this recurrence, when you study what this thing is doing, it has a deep combinatorial meaning. Mateus already spoke to you about Eulerian polynomials. Eulerian polynomials are defined using the descent statistic on the set on the symmetric group. Right? This is a descent. So you write your permutation. You take any permutation here, and then you write your permutation in the one-line notation. That means that you have I don't know. It's not a very complicated thing. So you have the two-line notation in a permutation, right? That says to you where you send 1 to 2, 2 to 1, and 3 to 3, right? So you forget about this because this is clear, and then you keep the one-line notation, and these are your sigma i's. And a descent happens when sigma I is bigger than sigma I plus 1. When you collect the descents, and then you take the cardinal, so you are taking out a lot of information there, right? We don't like to put information away, but the Eulerian polynomials, the univariate ones, are defined using this descent statistic. Right? They are the generating series, in this case it's a polynomial, of this descent statistic. So in this way you construct the Eulerian polynomials. So they carry combinatorial information, right? But they don't carry enough combinatorial information. We are killing a lot of information here because look at what we do. So we can try to carry more combinatorial information if instead of just the descents, we collect the descent tops. So at which point do the descents happen? So you take the descent top. And with that, take care here, this is important. 1, your permutation happens in this set. 1 can never be a top. 1 cannot be a top of anything. So 1 is there, but it's like a ghost. You know that it's never going to be a top. In this way, you collect more information, and you define these multivariate Eulerian polynomials. So now when you restrict to the diagonal, when you put these variables all equal to x, you recover in the diagonal the univariate Eulerian polynomial. But here you have more information. Here you collected more information about your polynomials. So what Branden did is to collect not just the descents, but also the ascents. And in this way, he builds a polynomial. He builds a polynomial an of xy, some other variables that we are not going to need. He builds a polynomial that when you study what this combinatoric thing does, is built in this way. This combinatorial sequence is built in this way, using a stability preserver. So you are carrying a lot of combinatorial information, a lot more than here, into these multivariate polynomials that are the ones that Branden defined. They are real stable. When you forget about the ascent tops, which is now you take the tops instead of the descent, what you get is a real zero polynomial. You can prove that. So you have one of the polynomials that you can fit into the relaxation, and now your polynomial has more information than the univariate one. Good. So we have several objects until this point. We have the relaxation, we have Eulerian polynomials, and then we have stability preservers, right? And now we finally increase the amount of variables that we have, adding more combinatorial information, not just taking the Renegard derivative. And then let's see what can we say about that. The roots of Eulerian polynomials, by themselves, they are interesting. People in combinatorics are interested about them. Also, people in analysis, they are also interested about them, because here I introduce Eulerian polynomials in a combinatorial way. But as I said at the very beginning, they appear in other fields. They appear in analysis for some applications about summation techniques and methods, right? So let's put name to the roots, right? And this is then, as the title said, extreme roots. So we are going to be interested in the extreme roots. This one and this one. There is a question in Math Overflow in which Christian Stump asked about the possibility of representing the roots of this polynomial, these numbers, in an algebraic way. This question is is too hopeful. Like these polynomials, why will they have a nice algebraic representation? This doesn't have to happen. But Stanley answered to this question with some estimate of the growth of these roots. And then when you see this is very weak, because there is here a n plus 1 root, and this is going to kill also a lot of information here. So I saw this answer, and then I wrote to Stanley, and I say, they are richer. I think your estimate could be improved. Do you know if you can? Because the proof that he gives, if he will have put a bit more of love in this proof, he could have improved it. And then he said, yeah, maybe an analyst can do that. He could have done that, because if you take a bit more of care in his asymptotic estimations, you can see that you get this that is much stronger. This gives you the asymptotic growth of the root. So when you fix a number k, and now you let n run, this is how your root is going to grow. Your kth root is going to grow. Yeah? Well, these are the extreme roots, the ones that are at the extremes. No, I mean, you have inequalities here, so the biggest one and the smallest one, they are extreme, extrema of the roots. Good, so we call improve the estimate by Stanley using basically his proof, a refinement of his proof, but then we continued reading because we were still interested in these roots. And this estimate is a point estimate. There were more people interested in these roots. Isban Metzo, in this book, combinatorics combinatorics and number theory of counting sequences, very interesting book, very interesting topic. He asked, not just for point estimations, he wants inequalities. He wants to be able to put these roots in a sandwich of quantities such that you can know exactly where the root lies. And then in this book, you can find that he gives this inequality. The first, this estimation, the estimation by this side of this absolute value of the extreme root, is a nice estimation. You can see that this estimation matches down for the extreme root. Now this is Q1. This estimation matches the estimation that we got, the point estimation one. But this one is very bad. This one here is very bad. Because you have here a linear term, right? This is not good. And you can also compute more or less how this, you can extract more asymptotic terms of this estimation. So then he asked about better bounds for this, right? And then we try to do that now with the new polynomials that we have. So now how do we do this? We apply the relaxation, and then we get this linear matrix polynomial, and now we look at the diagonal. So we are going to measure how good is the relaxation at approximating these Eulerian polynomials, looking at the polynomials from which we know a lot. This is the polynomials injected in the diagonal. So when we look at these polynomials, we look at the diagonal of the relaxation. So we set all the x equal, and then this is going to approximate the innermost root, because the relaxation is going to approximate the innermost root. But Eulerian polynomials are palindromic. So an approximation, an outer approximation for the innermost root is an inner approximation for the outermost root. Right? They are palindromic. So now we approximate this. We use we are going to use this linear matrix inequality. And how do we obtain bounds using that? Well, now when you have a linear matrix polynomial, and you know that the first matrix is PSD, you know that, and you know that it's a relaxation of your original polynomial, you know that for every vector that you take, you are going to have this inequality. You are going to have this inequality. Now in this inequality, you can rearrange terms, and then from this inequality, you obtain bound. You obtain a lower bound for this root. So this is how you proceed. And now you can see, you can apply this to the multivariate polynomials that we obtain through stability preserving. And if you do experiments in using Mathematica or any other method, you will see that you are going to get something exponentially better than the bound obtained using only the univariate polynomial in the relaxation. So you get this graphic of how the vector should look. Because you don't know how the vector, you have, now these matrices are very big, so studying them directly is very complicated. You cannot just take the determinant and study them, or try to directly study the linear matrix inequality. So you have to choose a vector. How do you choose this vector? You make a lot of experiments, and you ask in this experiment your program to give you numerically how this vector look. And then you get this graphic. You take, how do you get this graphic? So you take in each, for each n, you will get a vector of size m plus 1, because this is the size of your relaxation. You solve a generalized eigenvalue problem in each case, and then what you do is you take the interval 1, 0, and then you divide it in how many entries you have here. Then you divide it from, so 1 divided by, so you start, 0, 1, 0, 1. 0, 1, and then you start at 0, then you take 1 divided by n, till n divided by n, right? And then in each of these entries, you are going to put the entry of the compute generalized eigenvector for this generalized eigenvector problem. And this is how you generate this graphic. And this graphic, in this graphic, you can, if you put a lot of love into it, and you, and you look at it for some weeks, you will see that there is some pattern. There is some, you maybe don't see it right now. The first entry is a bit crazy, but this makes sense because the first entry of the relaxation is defined using monomials of degree 0. So the first entry of the relaxation is a bit different than the rest of the entries. So look, the first entry of the relaxation, the first row and the first column, and also the first slice of your tensor, right, is different. Huh? So then you expect that the first entry of your vector, of your optimal vector, could be different. You normalize the vector, so here is 1, right? But then the rest of the entries of your generalized eigenvector, they behave in a really similar way. So this is crazy, then there are some jumps here that you can understand. You will see what are the jumps. And then at the end you get a 1. You get a 1 in the tail, in the tail, right? In the tail you get that everything gets very close to 1. So there is nothing strange happening after some point. Then you try to build some guess, because now you want to compute an actual bound without using numerics. The numerics just help you to find what you need. So you guess an approximation of such generalized eigenvectors, seeing how they behave numerically. And looking at this picture, you can guess that for n even, so we keep more or less the notation. For n odd, you could also do the same. For n even, it should look something like this. This 0, don't care a lot about this 0. This 0 just is there because the first row, column, and the second, the one corresponding to x1 is going to look like 0 because x1 actually never appears. It's just there as a ghost because 1 is never a top of any descent, right? So you can put here any number. But then the rest of the numbers, this guess eigenvector looks like this. And you want to guess in a way that is algebraically easy to manipulate what you get. And this is very easy. What you get here is very easy. At the end, the tail is 1, and here at the beginning, you have some behavior that is understandable, and this y is a bit more wild, and you have to study it by itself. You have to optimize over this y. So now you do the optimization over this y using this vector. You go here, you plug this vector in each linear matrix inequality that you obtain, and then you study which bound you get for this multivariate, using this multivariate extension of Eulerian polynomials. And when you see that, what happens? Well, when you do this for the univariate, when you apply the relaxation is a real zero polynomial in one variable. When you apply the relaxation for this polynomial, for the univariate polynomial, you get some bound. And when you apply the relaxation for this multivariate polynomial, and then you normalize, or not normalize, you compute the bound associated to this vector that the relaxation gives to you, and you now compute the difference, you want this to be bigger than 0, you see that this is not just bigger than 0. It's when m goes to infinity is much bigger than 0. So adding more variables, adding this extra combinatorial information now, it radically improves the relaxation. You compare it with what happened when you just added one variable and the Renegard derivative. Nothing changed. Now you have here an exponential change. This is big. This is big. I mean, m is to n, so you could suppose that you have here a square root, but still this is bigger than 1. This is exponential. So, good. So we have now multivariate Eulerian polynomials, and we saw that when you pass from univariate to multivariate, this extra combinatorial information helps the relaxation. And Stump, Stanley, and Metzeau were interested in these roots. Turns out someone else working in a different field was some years ago, some decades ago, also interested in these roots. Sobolev wrote 4 papers about these roots in the 70s, I think. The 4 papers were in Russian. Fortunately, nowadays they are translating their collected works. And in these papers, he finds this estimate, this one, the better one, the one Stanley didn't know about. The thing is that he writes it in apart that the fact that it's in Russian, even if you spoke Russian, he called these polynomials in a different way, called them Euler-Frobenius polynomials, because these polynomials have different definitions. And he used a definition using the symbolic convolution, not the combinatorial one. The symbolic convolution, I think, is what you see in the recurrence is the symbolic convolution. It's some generalization of the symbolic convolution. And he writes this bound a bit differently. No, not this bound, this estimate a bit differently. It turns out that if you go through his proof and you take a bit more of care, he just write down this term. If you take a bit more of care of what he's doing there he uses this well-known method in numerics called some people call it the Grafes method, some people call it the Lobachevsky method. He's Russian, he calls it the Lobachevsky method. And the one that first introduced it was Dandelin. So I call it the DLG method. He used the DLG method, and then he obtained these bounds. As you can see, he just write down this, but if you take care and you check his proof, you can extract also this from the proof. You can extract also more terms. And when you, as you see, this is already very good. So the method that he uses is very good. And here you can establish the first asymptotic term, and here you can establish the second asymptotic term. And the third, you can establish it up to some constant. So this was already in the work of Sobolev, and Sobolev used the univariate polynomial. So but this Dandelin-Lobachevsky method, that's something strange to the polynomials. So the Dandelin-Lobachevsky method consists in taking this polynomial, taking your original polynomial p, you take p, and then you can consider this new polynomial. You can consider q of x squared univariate. This is going to give you, this operation is going to give you a polynomial in x squared. Now you consider this q. You consider this q, and you can see that the roots of this q are the squares of the roots of this p. You can study that. And the coefficients of this q, they depend polynomially on the coefficients of p. This is something nice that you can do. And this is what basically Sobolev does without calling it by that name. And he obtains already this. So I say, okay, if we have this for the univariate polynomials, let's try to apply the relaxation to what Sobolev does. So let's try to use the relaxation as an amplifier, because we see that when we give more information to the relaxation gives us more information about the roots. So now we build this polynomial, so we build a new sequence of polynomials. So we start with the Eulerian polynomials. We do this operation and we build these q's that have the roots, the squares of the Eulerian polynomials. And we apply the univariate relaxation to them. And when you do that with the univariate relaxation, the univariate relaxation powers the original method. Right here, you obtain these estimations, right? Here, you have this, and this is so this upper bound. This is now negative. This upper bound. Here you have something. You are summing something. It's a bit. Even when this thing is small, this thing is small, but it's positive. When you apply the method of Sobolev plus the relaxation, what you get is this. You get this asymptotic expansion of the root that verifies that, of a bound of the root that verifies that what follows goes to 0. So at infinity, this bound looks like this. With the -1 there. And if you check the root, numerically, you will see that at infinity, this root seems to look like this. So it seems like the combination of the Sobolev method and the relaxation gives you something so good that you are basically already at the root. The problem is that the relaxation only works in one direction. We cannot close the gap in the other direction just using the relaxation. But it already looks like this is the root. And this is very close to what Stump originally asked for. Because Stump asked for an algebraic expression of these roots. Okay, I cannot give you an algebraic expression, but I can give you an asymptotic expansion until a term that goes to 0. So it's very close to what the root should look and to what an asymptotic expansion could look. Huh? And now there are some questions about this. So the Dandelin-Lobachevsky Grafez method, when you give it, when you fit it with a real-rooted polynomial, it gives you again a real-rooted polynomials. So we are working all the time with methods that keep real roots all the time. What this says now is that it seems that whenever you have a method that produces a real-rooted polynomial from your original polynomial, you can always power this method a bit more with the relaxation. So if you have a method to approximate roots, there are books that have this method of a very famous tensor theorist, for example, Pan, from the University of New York. He has 2 big volumes about root approximation methods, right? So if one of these methods starts with you giving this method a real-rooted polynomial, and after that the method outputs you another real-rooted polynomial, you can now fit this real-rooted or real-zero polynomial into the relaxation, and it will power this method. So it improves what you get. And this tells us that the relaxation likes to be fed with combinatorial information. Information, theoretically, you can see it in this way. So the univariate relaxation takes the information of the univariate polynomial in the entries. When you expand this polynomial in a way that you inject the polynomial in something that has more variables, you expand the matrix. In this matrix, you add more combinatorial information. And you can recover the univariate information, doing operations, because the linear operators that we use at the beginning, they are linear operators. So if you undo inside the matrix this transformation that you do to obtain the univariate for the multivariate, the place in which this is injected, in this case it will be to take the all ones vector. In the all ones vector, you are again looking at the diagonal, so you are again in the univariate polynomial. So this information is contained. Information theoretically, your matrix contains always more information, right? So this tells us that if we take polynomials and increase the amount of information, we can always increase our estimations of the roots. Or not always, we cannot say always, because this is an example. But in many cases, it seems that it should be like that, because the original information is included there. So this will be the end of the talk, but not yet, because there are some other things. So this is how this kind of bounds that you get to look. So this is a computational problem. When you start obtaining these bounds, sometimes it's a bit difficult to see what's going on. So you have to sometimes feed it into Mathematica or something, some software like that. And sometimes this software is not able to give you correctly what is the asymptotic growth of this. So you have to take care. You have to look at it with care. They can get much bigger. This is for the univariate. This is the relaxation. So Metso used something called Colucci estimation. And the Colucci estimation is the thing that he used at the beginning to get this bound, and Colucci estimation is already, this estimation is already in the top left entry of our relaxation. So the relaxation collects other estimations. If you look at the top left entry, which is equivalent to take the vector 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, so you are there, you get Colucci estimation, which is what Meso used to obtain the term that has a linear term down here, divided by m, right? If you use the univariate relaxation, you get a 2 by 2 matrix, right? And you already, with that, you already get something that grows as it showed to be able to determine the first growth term. So this bound is obtained just looking at the best possible estimate by the univariate relaxation. In this case, you can use the best possible estimate because the matrix is small. With the univariate relaxation, you have a 2 by 2 matrix, so you can study it directly and you just solve the polynomial equation and you find the root. When you have more variables, you cannot do that anymore. Huh? Okay, so adding more information is helpful. The other way I say it, you can try to increase the initial tensor that we use. You can try to increase it adding more monomials of higher degree. And you have to take care because you want your initial matrix. So one condition that this is a mold moment matrix. This is the moment matrix that you are going to fill using the linear transformation. You have to take care because you need this initial condition to be satisfied. You need your initial matrix to be PSD. So if you fill it randomly, and you are not going to get a PSD matrix at the origin. You need this initial matrix to be PSD when you apply entry-wise the L form for the polynomial, for a polynomial P that is real 0. But for this one it happens. So you can find bigger tensors for which this initial condition is verified. Unfortunately, so this happens. Unfortunately, when you add the rest of the matrices that you will get in this way, now multiplying this matrix by x1, then x2, then x3, then applying the L form, and then taking, again, the first matrix plus x1 multiplied by the second matrix, so you obtain a linear matrix polynomial. When you do that, you don't get a relaxation. So you have to take a lot of care. This is very, it's very subtle, what you can do here. And the relaxation not only likes combinatorial information, it also likes analytical information. I say to you that if you add the Renegard derivative, that is an interlacer, is the easier interlacer you can think about, you don't get anything better. But if you add a different interlacer, for some, maybe all, maybe for almost all real 0 polynomials, when you add some interlacers, you will get something better. So this should not be written in this way. This should be that SP is included. This should be an inclusion. So this tells us that we need new forms of introducing new information into the polynomial using this transformation that add new variables to actually power the relaxation. And the last thing is that we use here the relaxation to improve the bounds that we know about univariate polynomials. But then we use this improvement to measure how well is the relaxation at improving these polynomials. It's a way of measuring in the diagonal what happens, right? These multivariate polynomials, the ones that the multivariate Eulerian polynomials, the one that you form with the descent tops, they are also interesting by themselves. And the relaxation gives you a bound for the roots, a global bound for the roots of these polynomials. And the study that we did in the diagonal tells us that close to the diagonal, not just the bound of the original polynomial is good. Close to the diagonal, by continuity, what you get is that the global bound, when you do small changes close to the diagonal, is going to be good. Because the relaxation gives you a global bound, gives you a multivariate bound, not just a univariate one. We just use the information in the diagonal to measure how good is that, because there is a lot we know about the univariate polynomials. So then to study, when you are in the, when you look at these polynomials, when you look at the graphic, right? These polynomials, here you have the origin, and this, every time that you increase, that you go the next step in the sequence, you will get more dimensions, okay? But let's see how this looks in the plane. So you get some roots, some ovaloids that are the roots. They don't have to be all convex. We only know that this first one is convex because it's a rigidly convex set. Rigidly convex sets are convex. I didn't say that, but this is why they are called that way. Now in the diagonal, you have your original univariate polynomial, and you have this root, and you have, let's say that there are more ovaloids, right? And then you have this other root. As the Eulerian polynomial A in one variable, this Eulerian polynomial is palindromic. This means that A equals, so let's say the one of degree n, is A equals A of it's palindromic. This is how we obtain from a bound here. There are colors. There are colors. Very good. For a bound here, an outer bound here, you obtain an inner bound here. This is how you do it. Because if you have a bound here and then the roots of these polynomials, the root, if R is a root of this polynomial, then as it is palindromic, 1 divided by R is the other root, and all the roots are negative. So this gives you another bound here. This is how you do it. Now, if you have more variables, you are now looking at this root here, right? So you are interested in knowing if there is also some kind of symmetry inside these polynomials that allows you to do something like that. And in fact, there is a symmetry. As these polynomials are less studied, this symmetry is new. People didn't know about this one, but when you do the generalization of what you will expect, the obvious generalization of what you will expect of taking the reciprocal of a polynomial, you get that this Eulerian polynomial is mirror reciprocal. That means that this root here transforms into this root here. So a bound here transforms into a bound here. What is mirror reciprocity? I'm going to explain what is mirror reciprocity. So if you have a polynomial P in several variables, let's do it, for example, so you can see it in a multi-affine polynomial. That means that all the variables are just to degree 1. When you do this, this polynomial is equal to, so let's write down the variables. This is equal to 1 divided by some monomial P. No, wait, this is not what it is. Some monomial P that makes what I am going to get into a polynomial, the smallest one. This will exist. This is the one in small, having the smallest degree. And here, so mirror is reciprocal, is mirror reciprocal. Here you will start at n and you will finish at 1. So this is a generalization, a multivariate generalization of being reciprocal. So you get also these symmetries in the multivariate case that you call exploit and study to establish roots, not just to establish bounds of the roots, not just to the univariate polynomial, but to the multivariate polynomial, to the extreme ovaloids. Close to the diagonal, they shall behave good because of continuity. So all this, I am about to end. All this tells us that there should be some nice way to explore this forest of polynomials, because now we have a forest of polynomials. We started with a sequence of polynomials, a sequence of Eulerian polynomials. Then we apply some transformation, some stability preserver that gives you another sequence that is real zero, is a real zero sequence. And we also have these other transformations using in numerics that take polynomials and then they transform them into other sequences of polynomials that also contain some, so if these polynomials contain combinatorial information, these new polynomials will also contain combinatorial information. But also algebraic combinatorial information. And we see that fitting that into the relaxation, studying these combinatorial relations, these new polynomials that search in this way, and using also stability preservers, then we can know more, not just about the initial polynomials we were studying, but also about the families of polynomials related with them, all the polynomials that now appear as sums of these polynomials in this big forest that we will have, and also about the roots. So studying all these connections between combinatorial information, stability preservers, the determination of roots, numerics, and using these polynomials as tests is what I call the Mindersee program. This is the Mindersee. It's a lake that is very close to the Bodensee, but much smaller. It's a nice place. The Mindersee program of exploring these connections, these relations between this combinatorial information and the possibility to establish good root bounds, maybe even exact roots, using this in combination with the relaxation. And with that, I will end. Thank you.
Thanks, Alejandro. Questions?
It's a question about your approach. Can you show us the definition of rigidly convex set again?
This is at the beginning. Here.
Okay, and why do you take away the zeros?
What?
Why do you take away the zeros?
Well, because I want this set, right? So I define it taking away the zeros from the space, and then I keep just the component, the connected component of the origin, because this will disconnect the origin, because these polynomials are not zero at the origin. They cannot be because of this definition, because of the definition. So they disconnect the origin from the rest of the space. This is why I take it, so I can define this set.
Okay, okay. And you told us that I think relaxation and restriction commutes. Can you tell us this again?
That it commutes. No, I tell you that when you take this new polynomial in which you are actually not adding new information, but you try to add in this way another variable, what you get is that the relaxation doesn't improve if you just do this. You need to fit this with more specialized polynomials for this polynomial, because you can build this Renegard derivative for each initial polynomial you start with. So this.
Thank you.
Yeah.
More questions?
Okay.
Well, if not, let's thank
Thank you.
Alejandro again.